Okay, then once again, welcome to this small workshop that I've called, but please no chart junk. What this chart junk means, I will explain in a second. My name is Matthias Magdowski. Usually I introduce myself with fancy titles that do not really exist today. I was not creative enough to come up with a fancy title, so I'm a scientific co-worker. This is what I do, or lecturer, let's say, at the Faculty of Electrical Engineering and Information Technology, like the student. And I belong to some institute for medical engineering, even if I don't do too much with medical engineering. And my research topic and the chair that I come from is electromagnetic compatibility. And electromagnetic compatibility, we are the reason why you are not allowed usually to use your cell phone in an airplane, because the electromagnetic waves of the cell phone could harm and interfere the sensitive electronics of the airplane. So that's what I do. Before we dive into the topic, the usual, I forgot to put this into the slides. I also finished the slides on very short notice, as usual. So if you want to have the slides, no problem, you can have them. I will share them with the people from the university library. I will probably also just upload them onto our OVGU cloud and share a post on Mastodon, maybe on Blue Sky, Threads, and maybe some LinkedIn, and also the recording there. So you never know if the recording works. Looks quite good. We will see. And if you have questions in between, feel free to ask questions in between. Yeah, and so we have roughly an hour. I will talk maybe, 30 minutes, maybe 45 minutes, and then we have some more time for some discussion without a stream, without a recording. And maybe, from my point of view, the most interesting thing would be to look at some examples of your work and to discuss this. But of course, then you need to share some examples. Thomas shared some examples in advance, but these are, of course, no good examples for bad examples, let's say. Okay, so why I'm doing all this? Because you are all writing a PhD thesis, papers, bachelor thesis, whatnot. And inside these theses, you need to use graphics to visualize your data, to show schematics. In electrical engineering, we have circuit schematics, but we do lots of measurements, lots of simulations, and we have somehow data to visualize. And so these illustrations, graphics, figures in written documents, papers, thesis, reports, and so on, they are kind of, let's say, the first-class citizens within these papers and reports, because just look what you do if you don't have much time, and if you are reading a paper or report or book or thesis, you skip through the pages and you are looking at the figures. Everyone is looking at the figures first, and then you are trying to get a clue what this is all about by looking at the figures. And that's why your figures should be good, they should be correct, they should be telling a story, and they should be not confusing people, they should look nice, because this is what people will look at first. And sometimes, from time to time, it happens that I think people put quite some effort into writing their text, into refining the text, and sometimes it looks like that the figures have been on very short notice, have been created without much effort. And sometimes then this chart junk happens. Okay, so at first I will try to briefly explain what this chart junk means and where this term comes from. And then we will, which is usually a good way to take a more detailed look onto some topic, look at some examples, and there are some extreme examples, that also happened in the real life. I think some of them are really made on purpose to be explicitly chart junky-like. And then I have some two real-life examples that, from my point of view, are interesting to discuss. And then, at the end, we can come to this part, how to avoid this in your work, in your paper, in your report, in your thesis. Okay, so what is this chart junk? What does it mean? It's a term coined by Edward Tufte, this guy, which is an American information scientist. And so he said, yeah, it's pictures where there is something that does not really contribute to the message, where content is confusing or distracting, that is unnecessarily decorative, so figures that are drawn in a way just to look nice, embellishing, and he says it's a waste of ink. So yeah, whenever we have something like this non-data ink, so this is from a book of him, The Visual Display of Quantitative Information. You can see this is already quite old. I think this is also an older picture of him. But this is his definition. I won't read this. I will give you some time to read it yourself and drink something. And sometimes, it's more like that people practice artistic skills instead of delivering their message and showing the data. Okay, so now we can, to more better understand this, take a look at some examples. And this is the standard Wikipedia example if you want to learn something about chartjunk. These are just the numbers, the powers of 2. So I think we have 1, 2, 4, 8, and 16. So this is the essential information, the power series of 2, displayed in this very decorative chart. But if I would tell you what is displayed there, would be probably very hard to see that, because these numbers without the background here and so on are very difficult to see. Okay. This is something that can happen because typical visualization tools that people might use, like Excel, which are not really scientific tools from my point of view, allow you to do something like this, to pitch your sales chart in a fancy 3D, and then something is flying in and zooming in and out. I mean, in PowerPoint, you can also do these animations. So I don't know how many data points we have in here, but lots of visualization just to probably show 15, 20 data points or so. This is, as you can see, something from Fox News. It's also probably not the most reliable source of information, but what is obviously the problem here in this chart? It's not adding up to 100%. So I don't know what happens here or what happened here. Obviously not a good idea. I mean, these pie charts, we will come back to this, in general are not a good idea because our human eye is not very good in measuring angles. And especially if it's a 3D pie chart, then it's kind of distorted due to the perspective view, so it's difficult to assess even the area then. But here it's simply not adding up to 100%. This is also a very nice chart. The average male height per country. And the problem is that the y-axis is not starting at 0. It's starting at to emphasize these size differences, but then the problem is if you scale these humans as if they would all be starting at 5 foot or 4.5 foot or whatever this is, simply does not make too much sense. This is something that I found in really some scientific journal. This is something from electric engineering, and what's the issue with this diagram? I mean, on first glance it looks nice, sure, looks nice and informative, but
overinterprets the difference because the numbers on the y-axis are quite small.
But this is, I think, gate drive loss comparison amounts to we have some semiconductor switch, and we are comparing 2 different technologies or so, gallium arsenide, and I don't know what the other git here means. And I think, so this one really has something like 0.19 something, and this has just 0.017 something. Here we have much less losses, okay, which is probably nice, but okay, we have, and it's just 2 data points. So we have a huge diagram with some x's here and some x's there and a 3D effect at the end just to show 2 values. A rather large value and a value that is 12 times smaller, 10 times smaller, something like this. This is what Edward Tufte means with waste of ink. We have just 2 data points and we use lots of ink and a scale here and a scale there and a 3D effect just to show these 2 data points. This is also something nice. This is from some German elections, as you can see, because there are the German political parties in there. What is the obvious problem here? And yeah, there's just a comment in the chat from Galvabart that says the 3D view is unnecessary in the gain-loss example in the one that we have just shown before. Yeah, exactly. So this is so the 3D effect is here just to make it look nice. So what's the problem here?
And that's not how a Venn diagram.
Exactly. This is not how a Venn diagram works. Yeah. So badly made Venn diagrams and badly made 3D charts.
This was correct. I mean,
this is
actually not the only one.
This is the example from Thomas. So I think here this is some different story behind this, because all the examples that I've shown you before have been created by humans, because they are sometimes 10 years old, 5 years old. They have been done before the invention of large language models and AI-based tools like ChatGPT, Google Gemini, Anthropic, Claude, and DeepSeek, and so on. And in the new ChatGPT 4.04, is it right, version?
Something I...
there are so many different versions right now, but I think it's ChatGPT 4.0 and then the subversion is 4.04. In this one, which has been released 2-3 weeks ago, when we have all seen the nice Ghibli style images in social media, they have all been created with this tool. It is also possible to create, or it has been possible before to create figures, but the quality drastically improved, also from my point of view. And I mean, here the background was there is, if you deal with mathematics and number series, there is this database of integer number series. I don't recall the exact name, and there's some kind of certain gap that small numbers are quite probable, higher numbers are quite probable, and then there is some gap in between. And I think here the task was to visualize this gap.
Yeah, so I input some text that was about the podcast episode, which was about this diagram. So it goes through some hoops, but I mean, these models are trained also on visual data. So I suspect that because there's this one iconic graphic that has been around for like 15 years on the internet,
which is showing this
dots in the bottom, and this color coding is also like in that graphic. That graphic somehow also influenced this result.
And the gap is essentially that these blue dots are less dense here, right?
Yeah.
Yeah. And this gap here, so there's the longer you look onto this picture, the more errors you spot. So this is also something. It looks nice and informative on first glance, but and the most funny thing is I have to translate this for our international audience because it's in German. So the real thing is about a gap in numbers, and numbers in German is Zahl. A Zahl is a number. So it's about Zahllücke. Gap is Lücke, and Zahllücke is number gap. And what ChatGPT made out of it, because it's more common, you find it much more often in the training material, is a tooth gap. If you are missing a tooth, then you have a Zahnlücke. But Zahnlücke and Zahllücke is sounds similar, but it's not the same. And so this is super funny. Also this Sloan's gap, and as you said, it's a gift that keeps on giving.
Yes. So have you seen that? So it has been apparently been getting much better at representing text on images. So I mean the headline, somehow the text looks okay, but then in the word Anzahl, it didn't put a small z. I mean, it's very hard to see from here. If you look at the left on the labeling of the y-axis,
Here.
Yeah,
Yeah.
it didn't put a Z, it put it to the upside down. If you look closely.
Yeah.
So this is my favorite.
Yeah, that's exactly. This is very hard to spot, but it's also that the X and Y label is the same. It's really funny. I love it. And the problem that I see, I mean, there will be other workshops here, and also your talk will be related to AI stuff. Unfortunately, very probably, we will see much more of this type of chart junk in the future. Unfortunately, scientific papers, student theses, reports, and so on will be full of this, and it will be a burden for the supervisors and examiners to spot something like this. Okay, so then let's have a look at some more realistic real-life examples. And the first example is you have done a seminar like this. There have been 50 participants, and you want to evaluate. I don't know. Is our university library doing some evaluation for after the seminars? Will some survey be sent to the participants?
I'm not sure.
You can organize something quickly. I mean, it's very easy to set something up on Moodle or Survey Legend or whatever. Yeah. So, but you have done a seminar. And you want to do some evaluation. So there have been 50 participants, and you spread some forms, and you got 30 responses, and the results that you got, you just ask one question with 5 selections, and 3 people said it was very good, 9 people said it was good, 10 said it was okay, 8 said it was bad, and luckily no one said it was very bad. Yeah, and this is the information to be displayed. These, let's say, 5 numbers plus that many participants and total responses. And the first question usually that you should ask yourself, like in some of the diagrams that we have seen before, is this really enough information that you require a diagram? And in this case, maybe not. It's very borderline. So what we could do is we could also just represent it as a table and put these numbers in a table, maybe calculate some share in some percentage, what this means, and then people could look on this table and get some idea on how well or how bad your seminar was received by the participants. But of course, such a table does not look nice. So what people might do, or depending on how you like tables, maybe also the table looks nice. For me, the table looks very nice because it's also made in LaTeX, like my slides. But okay, depends. So you could also, if you insert this value into Excel, for example, or in LibreOffice or in OpenOffice or whatever tool you like, you could also display this very easily as such a 3D bar chart. And then in this 3D bar chart, you have some vertical axis, and you have these items here, and then you get some, okay, there are some very good, more with okay, some in a similar size with bad, and yeah, here you're not really sure. Was this one person that says it's very bad? Is it 0 person? No one knows. Okay, so try to remember this diagram. By the way, so this means a bar chart looked from above, right? Always a bad idea. So this is also something similar. Gives me the chance to drink something. Mistakes in this graph, how many mistakes most people will spot, and probability that the first bar is lying. By the way, this is also a very nice website, Iran Science, if you like such science jokes and data visualization jokes. I strongly recommend to take a look at this website. There are some more chairs here in the front if you like. Just make your way through, but this way is not a good way because you will be walking through. But you can take this chair over there. Okay, so I've not really counted. I'm not sure how many mistakes in this graph are, but I think here there's also a hidden number mistake here. coming back to the chart, and I will go back in some slides before. So if you want to get something useful out of this diagram, we should be able to answer some questions from the data of this diagram. And usually it's a good way if, I don't know, you two remember the first question and you remember the second question, you try to remember the third question, the fourth question, fifth, sixth and seventh question, something like this. Can you try to remember your question? You got your question?
I'm not sure what my number is.
I think yours was 6.
Okay.
And maybe you can try to remember the 7. I can also go back and forth, no problem. So everyone got this question. And so now I will go back to this diagram. I need to cover this here. But now try to answer. Do you remember your question? And say if you could answer it from this side. How many participants were there?
So
difficult to say.
Yeah.
Could you answer this question from the table?
Yeah.
Yes. Okay. So what was your question?
How many participants gave feedback?
How many participants gave feedback? Can we answer this from the diagram?
No.
Not really. Can we answer it from the table? Yes.
Yes.
What was the next question?
How many rated very good?
How many rated very good? Can we answer this from this 3D bar chart diagram? Probably not. Can we answer it from the table? Yes, no problem. It was 3 persons and 6%. The next question was?
How many participants rating good?
How many rated good? We cannot also really tell, and we don't know what. So these numbers probably mean percentage. Yeah, but the unit there is missing. Okay, the next question.
I think how many, did a quarter or more rated as very good and
Rated as very good and good. Also difficult to say. So sometimes you don't care if people find it really, really good and excellent, or if they just found it good. You need to have 1 quarter that says it was good. Difficult to say. And the last question.
Last question was about proportion. What was the proportion of the answer very bad or very
Yeah. So none of these questions you can really answer from this diagram, but with 1 or 2 views you can answer them from the table. So this diagram looks nice, but it's not telling any information. It's not telling any story. It's not doing anything useful. It's probably confusing people and distracting people from this story that you would like to tell. Okay, so we can, I've written some arguments down here why this is a bad diagram. So some of them we have discussed already. So we have this 3D effect. The 3D effect makes it difficult to assess the height of the bars. Then no one really knows, is this absolute numbers, is this a percentage? Then these rotated labels at the bottom make it somehow difficult to read. So this very bad, the blue area that we have seen there, does this mean 0 or 1? And one question, for example, could also be, why are all these bars blue? Does this color have some meaning? Probably not. Okay. So a more suitable diagram, another way to represent this, so you now might argue with me, yeah, but this is a pie chart and you just told us 10 minutes, 15 minutes ago that it's difficult for humans to assess angles. Yeah, it's kind of a pie chart, but it's from my point of view still more than a pie chart, because every participant got the same chair in this ring, let's say. I would rather call it the ring diagram. And so now colors are somehow useful use. So the very good is something green, like the green light. Good is still green. Okay is something grayish. Bad is red. We don't have any very bad. And then, okay, the participants that not responded just get white, for example, because we don't know, we don't have any more information from them. And there are the absolute numbers and also the chair the chair given, and it's also somewhere stated in the center that we got 50 participants. And so now if we would go back to these questions, how many participants responded, how many rated good, how many rated very good, have there been more than a quarter that said it was good or very good? Yeah, it's about a quarter. It's probably not more than a quarter, but fairly easy to assess that it's something like a quarter. I don't recall all the other questions, but I think all of the questions now would be able to answer from this diagram. So it's a much nicer way to represent this information if you really want to draw a diagram, if you don't want to stick with the table. Okay, this is the second example. It's also from a German newspaper, Die Zeit. I think that still exists, and it's some older example. So the data in this example is really outdated, but the example is still nice. And now you might ask, yeah, but it's a German newspaper, why is the diagram in English? I translated it. Yeah, so it's not the original diagram. You can see that it's not a scan or something like this. It's redrawn, but I've tried to redraw it in the way as it was printed in this newspaper. And the story, so newspapers try to tell you a story. And the story is written here on top that coal so now we have much more renewables in our electricity generation. But at this time that coal was the most important contributor to the net electricity generation. And so the story is coal is the most important, and what is shown here is the energy mix. And then what is shown in more detail is the total net electricity generation in percent and in billion kilowatt hours. So billion in German is Milliarde, so 10 to the power of 9. Okay, and so then we have this pie chart and a 3D pie chart. And while I was talking, you already had a more detailed look onto this diagram. So what comments do you have now with the already kind of elaborated perspective? What is probably not the best thing at this diagram, except for it's a pie chart and it's a 3D pie chart.
So you have to add lignite and hard coal to make the argument about coal?
Exactly. So lignite is also some kind of coal. In German we would say Braunkohle or brown coal. And so the hard coal, which is the Steinkohle, and lignite make up together almost like 50%, and that's why coal is the most important contributor to the energy mix. But yeah, this is the story. It's somehow visible, but still somehow hard to get. Okay, what has someone else spotted something else?
Maybe renewables should have been green.
Exactly. So if we think about renewable energy, green energy, so the renewables are somehow bluish. Then I think the share of wind, this really does not make sense if you take a look at these numbers. So the total renewables is something like this, the 53 point something, and the wind is 55. So the 4.4% are of the total, not 4.4% of the renewables. So the wind thing here is way too small. We have much more, even at that time we had much more wind in Germany, because this is one of the main renewable energy sources. So renewables probably should be green. So lignite, what I've just told before, lignite is the brown coal. Why is the brown coal gray or black? And why is the hard coal, which is the Steinkohle, which is the black coal, this is brown? This totally does not make any sense at all, these two colors. Then nuclear energy, if I would ask you, what is the color of nuclear energy? yellow, because we all know this. I don't have a sticker of this, but then this very bright color of the natural gas somehow sticks out, even if it's not very important for the message here. And then, for example, I think this is a problem of the pie chart and of this 3D perspective effect, is that the area for the renewables, even if it's less percentage, is much larger, or looks, at least to me, much larger than the area of the natural gas. And for example, this lignite, even if it's just 2% more than the hard coal, is also looking much larger. So there are also many things in this diagram. So I've tried to summarize this here. I think we went through most of this. So the 3D effect itself shows no information, is only distracting. Then the areas are somehow distorted, and the color assignment is kind of confusing, at least. And this main statement that coal is important, it's somehow hidden there, but it's not directly visible from the diagram. Okay, and by the way, here I spot something that got not automatically translated in my slides. This should, of course, be e.g., not zum Beispiel. Okay. So maybe more suitable way to show this second diagram is to split this up into coal and others, and to say, okay, coal consists of this hard coal and brown coal, and the hard coal is gray, is black, the brown coal is brown, or the lignite, and then we have the others. And at this time, I think at the moment, we don't have any nuclear energy anymore in Germany. Am I right? Yes. So this yellowish nuclear energy now would be totally gone nowadays, but we have still probably kind of lots of natural gas, but we have way more renewable energies. And they somehow all add up, but just coal at this time was kind of important. If you would shut down all coal-fired power plants, there would probably have been a blackout in Germany at this time, at least. So I think now, if we would, not looking at to chartjunk or not, but if we would look at the very same diagram this year, probably renewable energy would be more than 60%, 70%, something like this. Which is, of course, very good for the climate. Okay, so now question is how to avoid chartjunk. And so some general recommendation is, in general, don't use pie charts. Pie charts are always evil. If you remember, pie charts are evil. You have already learned something. Then the next thing that is evil is 3D diagrams. 3D diagrams, except for you are doing medical engineering and you need to visualize fields, or I don't know, you do something in biology and you have surface diagrams and so on. So if no 3 dimensions are involved in the data, it's usually not a good idea to blow up your 2D information in 3D, then have this perspective view, because at the end your data or your paper only has also 2 dimensions. So 3D diagrams are also evil. Then don't use colors, shades, patterns, and so on without purpose. Today I've also seen 2 nice student presentations, but one student has, for example, also shown a bar chart to compare something, and each bar had like a shadow vanishing into the background. Like if there would be a very bright light coming from the front, and then each bar would have a shadow. It looks nice, maybe, not for me, but it's not adding any information to the plot. So don't do this. At least you have some purpose. And also, if you assign colors, don't do it randomly. Each color also has some message and draws attention, or you can use colors for grouping, do something like this. sometimes pie charts work, yeah. So who can work in science? Everyone. Also from Iran Science, a nice pie chart from them. I said sometimes pie charts make sense. Yeah, if you have a pie and if you want to show, okay, this percentage of the pie is still there, the other percentage already has been eaten, makes sense. Okay, I don't know what the blue color means, maybe, but this is not the way how it works. Okay. So, then looking at this from a more theoretical point of view, you should think, or you can think about attention and distraction. So, and to explain this, it's a good example is always if you read a book or if you read a newspaper. If you read a book, the purpose of reading a book is you read it page by page by page. You start at the front, you end at the back of the book. And so every page looks similar. If a new chapter starts, okay, you have a big headline, you have a blank page, a new chapter starts, and there might be headings of sections and subsections. But in general, all the font looks the same, and you can read through this line by line, page by page. You want to read the book, you want to read the story, you don't want to get distracted by something else in this book, in the typesetting of this book. On the other hand, if you read a newspaper, no one, at least not me, reads a newspaper. Okay, nowadays people don't read newspapers, but if you I don't know, open up some online newspaper on your big screen and compare it with a PDF of a book, there you have very many different fonts, and something is small and something is large and so on, and you don't read the newspaper article by article, line by line by line. You select, you want to read this article, there you just read the headline and say, okay, it's not interesting for me. There you read like the abstract or the teaser and then decide it's not interesting for me. But some articles, then you will really read all the details. And so the typesetting there is also to steer your attention and also sometimes, of course, to avoid distraction. And so these two principles, direct attention, avoid distraction, we can also use for diagrams. And so if we transfer this to graphics, to illustrations, strong contrasts, they always draw attraction. So you can, I've just shown you this slide 2 seconds ago. You can also try to take a look, or you can try to remember what you looked at first. Yeah? And even if we as at least European and Anglo-American people, we are used to read from left to right. And so even if this is on the left side, we would usually look at this first. Most people will look at this first, at this diagram here. Yeah, because at the right one, because this has more contrast. Our eye is somehow attracted to this one. Yeah, so strong contrasts always draw attention, attract attention. Then, yeah, if you have many lines in your plots, what people used before when there were no color printers available, they had dotted lines and dash dotted lines and very many different patterns of lines because the printers could only deal black and white. This is also very difficult, very challenging for the human eye to group. So I would not use this anymore. I would rather go for different colors because every monitor can display different colors. Every printer can print colors, no problem. Then complementary colors, they once again have a high contrast. They attract attention. Harmonic or harmonious, I don't know if this is the right translation, colors. Yeah, they. This is something that you will not look at first, yeah, but maybe look at later. And even some small pictures that you put inside the diagram might distract away from the actual data. So, yeah, if you create a diagram, the procedure is a little bit as when writing a report. I would especially if it's some kind of new diagram, something that you have not done before. From my point of view, it's always a good idea to just take a pencil and a paper, or maybe some like electronic drawing tablet, stuff like this, some Wacom tablet, and draw a quick sketch. If you think, okay, this would be a useful way to visualize these data or this data, and then think about what would be a suitable format and program to do this. Adopt the sketch, fill in the details, save it in a suitable format. This is what we will talk about also in a second. Then somehow integrate this into your written document, in your paper, report, thesis, and somehow revise it together with the rest of the document. And the most important thing at the beginning is this one here. What is the story that you would like to tell? What is the message that the diagram should deliver to your reader? Okay, so how much time do you need to plan? A lot, I would say. Yeah? So do it early in the process. Don't shift it towards the end, because this is what I've explained before. People, if they read your paper, read your report, they will look at the graphics first. So use as much effort as you use for the text, and especially if you have complex graphics with high information density. And okay, if you say, but I have just simple graphics, I need less time, it's probably okay, but no one wants to have simple graphics. I mean, no one writes a thesis and says, I have only written simple text. Yeah, that's not really the purpose of writing a thesis. Of course, even complex graphics or complex data that you visualize should be at the end as simple as possible to understand, but this does not necessarily mean that the illustration, that the graphic is simple. So most common error from my point of view is that there's some kind of, so from the editorial point of view, that there's some disagreement or discrepancy in appearance between text and graphics, and that people just ignore common rules for designing graphics. And to get this consistency between your diagram and the written document is, the best is if you do it in the very same system. If you do it in LaTeX, for example, nothing really bad can happen, because it will be the very same font, it will be the very same size. You can rescale it afterwards, no problem. But if you do it in some external program, it's always a challenge to get a similar font, to get a similar font size, to make it in the same appearance, and then you have to create them in the same size that you want to use later, because otherwise, if you rescale them, something bad will happen. And I think this happens, unfortunately, very often, that people write a paper, write a thesis, write some report, whatnot, have very nice illustrations, very nice diagrams, plots for the paper, and then they take the very same plots and put them in their presentation. And then maybe because they want to compare something, they put four diagrams on one slide, and then people only the committee members sitting in the first row in the PhD thesis present, they can read the numbers, and everyone else can just say, okay, might be something like this. So yeah, then the numbers are just too small. This is what you want to avoid. Also, if you do them in a, I don't know, you write your thesis in German, and then your professor later on decides, hey, this is such interesting work, we should submit this as a paper somewhere, but the paper is in English, but you have created your diagrams in German. Then it's still a very nice diagram, but the language is just not fitting the rest of the document. And most of this, if you do it in LaTeX, from my point of view, nothing bad can happen. Okay, so kind of a checklist for yourself. Make sure that the statement that you want to have is clear, that the factual content is correctly reproduced, that all the numbers and words can be are easy to read, that you have no misleading elements, and that the understanding for the reader is really improved. And I don't know how, so I would usually give this recommendation for a presentation that you have one message per slide, Maybe for a diagram, sometimes you have several messages into one diagram, but I would usually not do too many comparisons in one diagram. So this often happens in electrical engineering. Students measure something with respect to this and to that and to that, and then they want to do the comparison of each and everything into one diagram, and then it's just super confusing, especially in presentations. So is truncating the y-axis misleading? Yes, it is. In many cases, because here the y-axis also, here I've done the same mistake, but I just copy this. I need to reproduce this. So the y-axis here is starting at 98%. That's why, yes, it is misleading. So incorrect, incomplete axis labeling is also some kind of common mistake that we have seen before. There's also a nice XKCD comic about this. So the man says to the girlfriend, maybe you should give it another shot. And she says, no, our relationship is finished. We should break up. And I can prove it to you. And then she shows this diagram. And the man says, ooh, maybe you're right. And she said, I know, you are an engineer, you are a scientist, I know data can convince you. And then he says, no, I think that I can do better than someone who doesn't label her axis. So always label your axis. If you put axes in a diagram, please also label them. And the next very common mistake that I see is that people create kind of nice diagrams, but then save them in a JPEG format. And the problem is that, we all know JPEG format, because if we take our smartphone, and even if you take a dumb phone that has a camera, to save memory on the card, pictures are saved in this JPEG format. So we are using it, everyone uses it probably every day. Does anyone know what this JPEG stands for? Nice nerdy question. The people from computer science, you should.
Maybe engineering group or something?
Yeah, engineer expert, it means experts group. And it's an expert group that deals with pictures. And it's a group made of many people, so it's a joint picture experts group. JPEG stands for Joint Picture Experts Group, and it was some experts group that developed this compression format.
JPEG XL?
Probably
JPEG with smaller pictures. Smaller files.
30 years ago. And so who has ever heard of a Fourier transform or Fourier series? Okay, I expected some more, but okay. So what happens there in the background is that you don't save the actual picture, you do a Fourier transform of the picture, a two-dimensional Fourier transform, because the picture is two-dimensional information, and then you get the spectrum of the picture. And you could save the spectrum of the picture, this would be no problem, but then you would not save any space. So the saving of space happens because you throw away the high-frequency information of the spectrum, the high frequencies. This is what you save. And the problem related to this is, we will come back to this point later, I need to skip my slides a little bit. The problem is that due to this JPEG compression, so there's a book about this. No, there's no real book, this is also just some fake book cover. But the problem is that every time you have sharp edges in your picture, if you have a jump from white, black, and so on, these are sharp edges. This is short, let's say, in time domain. This is broad in frequency domain. So all these sharp edges contain a high frequency information. And this is what is thrown away. So usually in JPEG compression, you get these compression artifacts all around. And this is, of course, not good. What you want to have for diagrams, figures, for line art schematics. So First thing, raster graphics is bad, and even worse is save these raster graphics in a JPEG format. So raster graphic means the picture consists of single pixels, and each pixel has a grayscale color or has or a grayscale value or a color. And the problem is, so I've tried to demonstrate this here on a German bus stop sign. If you scale in, if you zoom in into such raster graphic, it will not look nice anymore. Instead, a vector graphic consists of single geometric elements. Like for this bus sign, we need to have a yellow circle or yellow ring, a green ring on top of it, some yellow circle in the center, and 3 rectangles to form the sign. And so the good thing is, if I zoom in here, I can arbitrarily zoom in, it will always look nice because it's a vector graphic. You can rescale them without problems. If I zoom into the raster graphic here, pixels will just grow larger. And usually you want to have something like this for your plots, for your diagrams, because you want to show them on the screen in a different resolution, on a bigger screen in a different resolution. You want to print them on paper, you want to print them on a large poster. They need to be rescaled. And this only works with a vector graphic. So here's some nice cartoon that for the web, most browsers nowadays it's getting better, but if you publish something on the internet browsers and also browsers on your smartphone usually won't care about vector graphics. So there you need to go to a raster graphic format, but then this PNG, which stands for Portable Network Graphics, is much better because it's a lossless compression. It does not introduce these nasty compression artifacts. And it only works for pictures with few colors only. So the PNG format would not work as nicely for your smartphone photographs, but for this it works. And so here you can see, if I zoom in a little bit, this is raster graphic without compression artifacts. This is the JPEG compression. And I've written some article, not in electrical engineering, but on higher didactics about half a year ago, and now it's being typeset and being printed. And I got a response back from the publisher that they are just accepting JPEG files for figures. And I was really, really, really upset about this. And I will send them, if the recording works, I will send them my recording too. Make them aware of this problem and ask them if it's really a nice decision for if you want to print a book to only accept JPEG files. Because at the end it might look like this. Okay. So then what can also happen is I've reviewed a paper recently, and I just show a very, very small zoomed section of this paper. So of course the diagram is much larger. And as you can see, it's also this raster graphic. And then I've written the authors, hey, your figures, okay, so from the content they're okay, but please use a vector format because it will look much nicer when being printed. And so they sent a revised version, it would still look like this. And I told them once again, hey, I'm really serious on this. I want to see vector graphics in your paper. And then they sent me this. So what happened here? They kind of vectorized this diagram. So they took their bad raster graphics and put them into some program. Probably, or maybe they asked ChatGPT for help. This is what Thomas suggested. And then, of course, there is software available also since decades on the internet that would vectorize your graphics. But as you can see, now it's just a path. And this is not the same star pattern here and there because it's made from the ugly, distorted pattern before. And you can also see it at the letters that it's not really the letters T, H, and E. It's a path that somehow shows these letters. So not really good. So more common mistakes is, as already said, too small tick labels, also strange number format, if you do simulations or calculations in MATLAB, in Octave, in Python, then the output format of these programs is often something like this, which is okay for output of a computer program, but it's not what you want to print in your report or in your diagram. So it probably might be, instead of saying it's 2.345 e minus 007 meters, it's probably better to say, okay, it's 3.2 point something 10 to the power of minus 2 meter, or maybe it's better to say it's just 2.3 centimeters, because this is easy to understand, at least for people that are familiar with the metric system. I've also recently reviewed a paper where it said, okay, we have something that has, it was about some antenna alignment, and we can hit in 3 meter distance, we can hit a spot with a 6-inch diameter. This is what I like. So in 3 meter distance, it's 6-inch diameter. But yeah, 6 inches, something like the span of your hand. Okay, and some references. So there's a very nice handbook manual, something like this, of this TIX language, which is the language that is used in LaTeX to draw figures and diagrams and plots and schematics. It's a stupid German abbreviation, some recursive abbreviation, meaning TIX ist kein Zeichenprogramm. TIX is not a drawing language, but it's a drawing language at the end. And there's one chapter, Guidelines on Graphics, and you will find similar examples there. And so what I've tried to explain you in this section, and maybe also some parts here, in a better and elaborated way. And then there is a nice book from a German couple, Lutz and Heike Hering. I think and the German version is something of course not how to technische Berichte toll schreiben oder irgendwie sowas. And so the nice thing is that this book is available in English and in a German translation, and it's from Springer, which is somehow okay. But the good thing about Springer books is that you can download them from within the university network as a PDF file and read them, which is very convenient and handy. And so this is a book that I usually recommend because it's accessible for the German students and it's also accessible for the international students. And there's, so the whole book is about how to write technical papers, reports, thesis and stuff. But there's also a chapter and section just on figures. So this finishes my presentation and my talk. And now I stand like the squirrel, and I will stop the stream and stop the recording.